All right. Hello, everyone. Welcome to the Off by One security stream. Okay, so before we get started here, just a quick check, make sure everybody can hear me and see me okay. I like to do that at the beginning of every time in the hopes that we get off to a good start here and don't have to worry about troubleshooting our AV again. But right now, you should see a Microsoft Paint screen up and just my camera. And let me jump over to a VM here that we're going to be using. Okay, great. Thanks, Emil. Thanks, HDR. Great. Cool. So, what I want to do in this stream, in this session, if you saw my tweet out there, is take a look at a C. So this is something that I've been teaching for a long time, right? And a lot of people will email or DM and say, "Hey, what's the best way for me to prepare for taking a class?" And it might be one of my classes, it might be a class from offensive security or someone else, Corland code or whoever it is. And a lot of these courses require that you come in with the fundamental understanding of maybe C or C++, and then some basic reverse engineering skills so that you don't have to worry about struggling to try to catch up or keep up when you're doing the labs. Like if you've got that prerequisite stuff out of the way, then we can get to the good stuff faster. And I know just having worked with a lot of people over the years as well, a lot of information security professionals have scripting language skills, but not always development language skills, like in a lower level language like C or even something like Rust. But which is fine. But what an interesting thing that manifests is I see a lot more security engineers who want to get into hacking or who are doing hacking. And by hacking, I'm talking about like reverse engineering and exploit development and bug hunting. I find them seemingly being more comfortable with looking at disassembled code versus looking at pseudo code. And that comes from that lack of knowledge of having the background in C and C++. If you're more comfortable in disassembly, if you if you talk to a developer who is proficient in C or C++, they're going to say that's crazy. Why would you ever be looking at disassembly? It's going to take you so much more time versus looking at the pseudocode, which is often true. Now, pseudocode and decompilers aren't always perfect. A lot of times there's mistakes, there's cleanup that you have to do, but as you get more comfortable with it, you can clean it up faster. And also it helps obviously if you've got symbols and such to support you. But you look at some examples where if you take something that's been disassembled, like a function that's been disassembled, let's say that there's 40 lines of disassembly in a function versus if you decompile that, it might only be like 4 or 5 lines because there's so much more. Like you think about like functional programming, if you know what that means. Like we kind of pretty much have to say exactly what we want you to do. We can't make any assumptions. Like a silly example, if I tell you I want you to enable RDP on a remote system, terminal services, so that I can remotely connect to it and work on that system, I would assume that if you enabled that, that you might also go in and log in, make sure that you can authenticate, make sure it works. Don't just turn it on and assume that it works. Validate that. Like that's kind of what I'm getting at. If when you're going from a higher level language down into like assembly or a lower level language, it gets a lot more specific, a lot more lines of code oftentimes because you have to say exactly what you want to happen. A compiler is going to compile your code into assembly and then assemble it into machine code. And there's a lot of optimization, there's a lot of inferring going on. And if you look at your code in disassembly, sometimes you'll even say, well, why is it doing that one thing when it's not even necessary for that thing to be happening? Like, I'll show you some examples as we go through. One example, like I just saw the other day again. You're on a Windows system, and let's say, for example, you want to locate the PID, the process ID of the program that's running. So in order to do that, one easy way to do it is in user land, depending which thread you're under, it doesn't matter which thread you're under, but whatever thread you're under, you dereference the FS segment register and various offsets. So the segment register FS on a 32-bit Windows application or process is pointing to something called the TIB, or the thread information block. On 64-bit, it's the GS segment register that does that, but that doesn't really matter. The TIB is a structure. that every thread has. It's a userland structure, and it just stores data that's useful to the thread. Things in there are like a pointer to the structured exception handling chain, the address of the stack base and the stack limit for that thread, because every thread gets its own stack. Everything's in there, a pointer to the process environment block at offset 30 from the segment register FS if on 32-bit. And I know I'm rambling a bit here, but my point though is at a particular offset, I forget what it is off the top of my head, but a particular offset inside the thread information block, that Windows userland structure, is the PID, the process ID is there. So when you look at the function that actually gets the process ID, so there is a Windows function that's get the process ID. And when you look at the actual function's code, the first thing it does is it dereferences an offset in the segment register that is the full 32 or 64-bit linear virtual memory address. Because segment registers can only hold 2 bytes or 16 bits. So they're not capable of holding a full 32 or 64-bit address. So my point is, the first thing it does is it dereferences, and by dereferencing, if you're not familiar with that term, we're going to the address and we're taking what's there, and we're loading that into a register, a processor register. And then after that, it dereferences yet another offset from that address where the PID is stored. The reason I said all that is because that first instruction wasn't necessary. Why dereference the full linear address and then dereference from that same address a different offset to get the PID? Why not just dereference the PID offset to begin with? Like, that is an example of a compiler made that decision for you. And my point is just, when you're writing in these lower level languages, you've got a lot more power, you've got a lot more speed potential. You're cutting out all those decisions being made by compiler. All right, so don't worry about what I just said there. That was just a little bit of a rant. But my point for that one is, I started off by saying people tend to be a lot more comfortable with disassembly versus decompiled code. And that's it's an interesting phenomenon. But once you get more comfortable with C, C++, you'll find yourself looking at the pseudocode, the decompiled code, a lot more often, and it'll speed you up. But there are times you have to know both, because you can't always rely on the decompiled code. So more on that later. I jumped ahead. Let's go back to the beginning. What I want to do this session for, again, is to help those of you who either are preparing for a class or just preparing in general to dive into reverse engineering. And we kind of have to start from the beginning. And I thought about, like, what should this session look like? Because this means I have to have multiple sessions. I can't do it all in one. So if we're going to start at the beginning, one of the things I would suggest to people who have asked me in the past, how do I get started in reversing and getting comfortable with IDA Pro or Ghidra or whatever it is, Binary Ninja, Hopper, I always say, like, take Hello World in C and compile it in its most simple form, and then disassemble it, and maybe decompile it as well, but just disassemble it. And look at the main function, because that should be the only function that exists if you're just doing Hello World. And look at the few lines of assembly or disassembled code. And that's what we're going to start off doing. And then I want to add some complexity. We'll change it from saying void main to int main. What's the difference? And then we'll change it to, let's use the argument counter and the argument vector, and let's see how that is sorted on the stack. Like, where is it? How do you know it's there? How do you know it's being used? If the program is stripped, how do you know where the main function is? There's a lot of easy little tricks that you can do, but then we'll ramp it up a little bit more, and we'll allocate a buffer, and we'll look at the procedure prologue and epilogue and just some basic things that the compiler inserts in based on the calling convention you select, like cdecl or standard call. And then from there, we'll see how we are in time, but I maybe we'll do something on the heap, and we'll do a malloc call. So we call malloc and we pass it a size. It returns back to us a pointer. Well, by default on Linux, in my experience, if you just call malloc and you hope to get an address as a return to where your allocation was made, you probably want to go check to make sure that there was no issue with that malloc call. If what returns back to you is null or something that's not a pointer to the allocation that you just requested, then it failed. So what does that check normally look like? Things like common instructions you see in when you disassemble code, like the test instruction. Test. You'll see something like test, racks, racks, RAX, RAX. And like, well, what is that doing? Well, it's checking to see if the register holds a 0. Why? Like that's the kind of stuff that I want to talk about. And we'll move up from there as we go forward. And I will try as I go through this to make sure I check the questions, but it's going to be hard for me to always take a look at that if I'm in the middle of something and I want to get through things. But I do want it to be interactive, so I will try and look at the questions. It's on a different screen. If I don't see it, just write it up again, maybe a little bit later, and I'll make sure I follow up on that. So we'll start off doing this kind of stuff, and then in the next session, maybe we can do things like use IDA Pro and look at things like IDA scripting. We can look at doing dynamic or static analysis. We can look at things like I saw somebody mention flirt, like a flirt signature. What's that? Well, a flirt signature is heavily used by oftentimes capture the flag teams, as well as other folks like malware, reverse engineer folks, and things like that, where a lot of times, when we compile our code, we typically compile the code dynamically so that there's dynamic dependencies, meaning that I know that my program has a dependency on your operating system to have libraries which can export functionality that my program needs versus statically compiled a binary. If I statically compile it, all the libraries, all the dependencies are statically compiled into the binary, making it much, much larger. And if we do that and we strip it, so think about that. I'm doing a capture the flag. If I'm writing a capture the flag challenge, right? And I want to make it challenging for you, or at least a little bit more challenging. My capture the flag challenge might only have 5 functions that are internal that you need to care about. Maybe stir copies called or something like that. So to make it a little bit more challenging, what I'll do is statically compile some modules into the binary so that when you go and look at it with the disassembler, you see thousands of functions with no names instead of the 5 functions that you need to care about. So if you know how to write your own flirt signatures, what you can do is take the different versions of libraries that are out there, and you can look for patterns inside those libraries or modules so that if someone statically compiles a binary, if we have the flirt signatures associated with the libraries that are statically compiled in, flirt will allow us to mark that as library code. And then what we'll be left with are the 5 internal functions that we care about again. It's a huge time saver. So you'll see that a lot of capture the flag teams out there, they've got big flirt databases because it's a huge advantage in CTFs. It's a lot of work creating them too. It's tedious to do so. All right, so let's dive in here. The first thing we're going to do is just write a little program as basic as possible to do hello world, and we'll look at it in the debugger. And we want to look at things like how to identify the entry point and all that stuff. So again, if you know how to do basic x86 64-bit reversing, a lot of this is going to be pretty redundant, or you've seen it before, but that's why we're starting at the beginning. So first thing we'll do is just create a little program. I'll just call it hello.c. All right, so one thing we have to obviously understand or know is what header files do we need to load in here that we need to use? Well, a lot of times the compiler will tell you if you didn't include it. In the old days, it really didn't help you that much, but in newer ones, it should tell you, hey, you need standard IO, standard lib, whatever, string.h. So I'm just gonna, since I'm only gonna be calling printf, I'm just gonna go standard IO. So we'll say include, and then stdio.h. And now I'm gonna say void main. Now you typically wouldn't say void main, at least that's not what you're taught, because you might want main to return back a status code like a 0 if it's successful. And that's one thing to point out. Like I'm gonna be randomly saying things all the time, and maybe take notes if you want to remember this stuff. When you're looking at disassembly, there's a bunch of different registers. There are 16 general purpose registers on a 64-bit x86 Intel, whatever, AMD processor. So on the x86, which is 32-bit, not x86 64, on x86, there's 8 general purpose registers. And you've heard of them before. Things like RSI and RAX and RDI. If you see the R there, that's 64-bit. If you see just EDI, ESI, ESP, that's extended, that's 32-bit. But what I was going to say is one of those registers is the accumulator register. It's AX, either RAX, RAX on 64-bit or EAX on 32-bit. That register is what's going to return back from a function call something like a status code if that's what you're expecting. So a lot of times we might use constructors and destructors. Those are going to be things, there's these sections that are going to be part of, in this case, the ELF binary format. ELF is what we're going to be looking at today because that's Linux, the executable and linking format. That's the object file format for Linux binaries. So there are these different sections in there, like you'll see start and fini, which are detours, ctours, things that you can say, I want these things to happen prior to handing over control to the main function. So the first thing that happens is we go to the entry point. We load up the process. We start allocating all the sections, all the default stuff like the stack and the heap and all that. This code executes before ever handling control over to the main function, which is the first function that you wrote. So ctours, constructors, are things that happen before we pass control to main. And then detours, destructors, fini, that's going to be things that happen when you go to terminate the process before it terminates out. So back to the point, if we said int main, then we're going to be expecting likely a status code to be returned back, like a 0 if it was successful and a 1 if there was an error. We'll get back to that in a moment. It's just our declaration stuff. So I'm going to say main void here as well, meaning that I don't expect any arguments to be passed to main. What we'll do in a little bit is use the argument counter and the argument vector, which those are, if we're expecting things like command line arguments, like ping, for example, ping wants you to give it an IP address. So that's going to be an argument that comes in. We'll get back to that in a moment, but right now we're not taking in any arguments. So I'm just saying void main void. So next, we're going to dive in and just simply say printf. And something interesting here I'll show you as well. Again, we're going to be talking about lots of different things, so please do take notes because it's going to be kind of random. Right now, that's just what popped into my head because when I see printf, you're going to see something weird happen when we compile this, and it's not going to use printf. It's going to use puts, and we'll talk about why that's the case in a second. So I say printf hello world, not hell world. Sometimes it is. All right, so I'm going to just, I'm not going to put a new line in like you normally would. I'm going to close that out, and then I'm not even going to put a return or an exit. I'm just going to kill it right now. That's the simplest that we can get. So I'm going to go ahead and get out of here. So we'll write it out, and then we'll just use GCC. Now I'm going to say no pi. Pi is a exploit mitigation that stands for position independent executable. What it does is randomizes the image. The executable itself is going to be default randomized because of address space layout randomization. If I say no pi, then it's not going to do that. The libraries and things like that and the stack and the heap, those will still be randomized. That setting is based on a flag. We'll talk about that later. But right now I'm going to say no pi. And that's going to make it so it does not randomize the base image. And we'll see that soon. I'm also going to say, actually, I'm not going to say anything else right now. All right, we compile that as expected. It's not very complex code there, right? So it's just compiled. And then we're going to go ahead and do a couple of things. First off, this program is not stripped. So if I say file, hello, you can see at the end there, it says not stripped. That's useful to us doing reverse engineering because that means all the internal symbols and such, like the names of the functions, are not going to be removed. We'll be able to say disassemble the function name like main, versus if you strip it, all that stuff gets removed because the process doesn't need it to run. The thing that you can't strip are the dynamic dependencies. So in this example, you saw that I use printf. Printf is going to be a dynamic dependency. We have to link that. We'll talk about what linking is too. So right now I'm just going to do something real quick. I'm going to show you what strip means. So if I go in and I say, let's do this first, read elf. It's a little tool. I'll say minus all, everything. It's going to read through all the section headers. And the program name is hello. And we're just going to grep for the word entry. What that does is it shows us the entry point to the program. So this is useful, especially like if it is something that's stripped. You'll see that there's a call to something called libc start main or whatever. And that'll get stripped sometimes too. But there's a real easy way if it is a stripped binary and you don't know what the address of the main function is, because that's the first function you're probably going to want to look at, that you can do it. So the first thing you might do is this right here, read elf minus a hello grep entry, shows you the entry point. There's other ways to see the entry point as well, but this is one simple way. And then we're going to say obj dump, which is a disassembler on Linux, minus d for disassemble, minus j for section. .text is the code segment. That's what we want to disassemble, is the code segment. The program name is hello. And then I'm going to just pipe it to more. So you can see start is the first thing that comes up in the text segment. And that is that entry point address that we just saw. So there's that entry point. Now look towards the bottom of this block here. You see that there's a call quad word. So call a 64-bit address. And right above that, there are 3 arguments being passed via the registers. Now, one thing to look at here is something called the disassembly syntax or disassembly flavor. Right now, we're seeing it in AT&T syntax. Most people like Intel syntax, but this tool by default shows you in AT&T. So does the GNU debugger. You can change the disassembly flavor, totally fine. Most people go with Intel, but right now this is AT&T that we're looking at. And one of the main things to know about the differences between AT&T and Intel is that the first thing you have are the instructions like XOR and move and pop. After the instruction are the operands. So in AT&T, the operand is first the source, second is destination, if there are 2 operands. So you can see the top thing, it says XOR the source EBP, comma, against the destination EBP. That's just going to zero out the register is what that command's going to do, or that instruction's going to do. But look at this other one down here. It says move is the instruction. Basically copy the contents of the RDX register into the destination R9 register. Moving it does not cut and paste. It doesn't move out of one into another. It just copies from one into another. But that is an example of AT&T syntax, where the source and destination operands are kind of more intuitive because you think first source, then destination. If this were an Intel, you swap the source and destination operands. So you'd be saying move into this register, comma, that. We'll get back to that because I'm going to switch it over to Intel syntax when we go inside of the GNU debugger. But look at the bottom here. Again, there's 3 arguments being loaded into these registers, and then we're calling something, right? What we're doing is, this is libc start main. So that last argument, this one right there that I've highlighted, the 4004E7, that is the address of the main function. So if we scroll down a little bit, 4004E7, right there it is, and you can see it's the main function. So back to my point, if we strip this binary, you wouldn't see main and stuff in there. So how would you know where the main function is? That's one way of doing it. And if you load this into a disassembler like IDA or Ghidra, a lot of times they'll be able to figure that stuff out automatically for you. But let's look at the difference here. If we quit out, and if I now say strip hello, and we do the same thing, see now how we don't see a reference to libc start main down here? We still see that call to the quad word, and we see those 3 arguments. So that is still the main function. But if we scroll down now to 4004E7, right there, it doesn't say main now, but that's the start of the main function. So it's just an example of how to find that. Again, there's multiple ways to do everything. So you'll hear sometimes people say, why don't you just do it this way? It's like, well, yeah, we can do it many different ways. That's the great thing about it. But I'm going to recompile that so it's not stripped for now. and we're going to load it in the debugger. So I'm going to say gdb --nx. What that means is no extensions, because right now, if you've got something like Jeff or PETA, some kind of exploit development extension, that's going to tell it not to load. I don't want it loaded right now because I just want to see everything just kind of raw at the moment. And then next up, we say the program name. So hello. Great, so now it's loaded in. I just hit Control L to clear the screen. Oftentimes, one of the first things you're going to want to do is say info functions. And this is going to show you all the dynamic dependencies, which again are the things that my program has a dependency on, like printf in this case, because we didn't statically compile it. So what you see is when it's a dynamic dependency, you'll see @plt after the function name. And we can't strip those typically, because if we strip those from this table, then how does the process, when it's running, how does the linker and stuff know what you need as a dependency? So that's why we can't strip that. But what we could strip are all the things that are internal, like main and fini and start. Those would all go away. I'll show you again real quickly. If we drop out of here and say strip, and now we go back into GDB and we say info functions, that's all we get is that one dynamic dependency, which is printf. So that's a big difference, right? It's going to make it a little bit harder for us to reverse because we don't have the internal symbol names. If it's a complex program, it's going to make it a lot harder to reverse because usually function names are named something that's very useful or meaningful to anyone who has to read that code and understand what it's doing. So if we strip it out, especially like with malware, it becomes very complex at times. So I'm going to drop back out and we're going to recompile it without it being stripped, bring it back into GDB. Info function. So first thing I'm going to do here is disassemble the main function. So we'll say disassemble main. This is default in AT&T syntax again. So what we have is the source operand first, followed by the destination operand. Some other differences are things like the % and the $sign. You don't see those in Intel syntax. Those are specific to AT&T. Intel will actually spell things out a bit more, like the double word pointer. It literally says that. There's other differences as well, but let's just switch over to Intel because I don't want to use AT&T. So we'll say set the disassembly flavor to Intel. And now if I say disassemble main, see the difference? The source and destination operands are reversed now. So in AT&T, we'd say move this into that. Down in Intel, we're saying move into this, that. All right. So what I want to do now is walk through each of the lines because this is as basic as we can get. So we're starting from that. Like, let's go through every single line of disassembly here so that when we then go and change things like make it int main instead of void main, and we use things like the argument counter and vector, you'll see the delta or the difference. And then we can reverse that as well. All right. So first thing that's happening here, this is the procedure prologue. So this is something that the compiler is going to automatically insert for you based on the calling convention selected and other factors. Another thing to point out is these registers, they're called general purpose registers. Now, some of them aren't general purpose. For example, the instruction pointer, that's not a general purpose register. That is the register that points to the next virtual memory address where code execution is to continue. It's called the program counter. That's not a general purpose register. But the ones like RSI and RSP and RBP, they're general purpose. There are some that have notable use and they have a specific purpose. For example, the stack pointer always points to the top of the current stack frame. So that's a register that does have a specific purpose. Always point to the current stack frame, the top of it. The base pointer, this RBP register, on 32-bit, it's pretty much always used as something called the frame pointer. It basically, for the duration of a function call, the base pointer points to a static position within something called a stack frame that we'll talk about. And the reason it points to a static position is there's a couple reasons. One is so that we can tear down the stack and that when we're done with that function call, we need to tear down the stack frame. It allows us to tell the stack pointer where it needs to be and things like that. The other big factor is it's used for local variables and arguments that are passed. So if we want to pass a couple arguments to a function, how does that function that's been called know where the argument is? We can reference the base pointer. But on 64-bit, we often will pass arguments via registers and not via the stack. I mean, we still may, but oftentimes we don't, because it's safer to pass arguments via registers if you think about it, because if we're pushing things, if we're pushing arguments into memory in a writable region of memory, if there's an overflow opportunity, then an attacker could potentially overwrite those arguments and modify them. If they're in a register, you can't overwrite registers. You can use instructions that'll modify the registers, but you can't overwrite a register. You'll hear people inaccurately say, I overwrote RIP or I overwrote EIP. You can't overwrite EIP or RIP. You can overwrite a pointer on the stack or in a C++ object, and maybe via instructions, we pop something into a register to modify it, or we return to an address redirecting the flow of execution. But you didn't overwrite the instruction pointer, you overwrote the return pointer in that case, or a function pointer. And then due to some code execution, you were able to modify them in that manner. So again, I do see a lot of things flying by, and I'm trying to stick to a certain course, and then I'll take a pause to look at some questions. So this first thing that's happening up here, like I was saying, is the procedure prologue, and that is setting up the stack frame. Every function call gets its own stack frame. Every thread gets its own stack. And typically we work with multi-threaded programs or processes. So the procedure prologue, let's say we start a program and we're in the main function. The main function, like you see in this example here, see how in the main function, we're going to call printf? That means that we need to build a stack frame on top of main's stack frame on the stack. So the procedure prologue is what builds the stack frame for a function that's been called, and the procedure epilogue is what tears down the stack frame when we're going to clean it up. And again, that's compiler inserted code. So all you have to know right here, for those instructions, those two lines, that's the prologue that sets up the stack frame. And then if we go down to the next line, it says LEA, load the effective address. Now this is in AT&T syntax up top, so let's go down to the bottom here. Load the effective address into RDI, because our destination operand is first. Then go to the instruction pointer, the address that's stored in the instruction pointer, plus 92, and we want the address of that. So what that's going to do is actually go out of the bounds of the code segment, likely to a segment that is adjacent to the code segment. If you were to write out the default way in which you would see memory, I don't have my pointer with me sadly right now, you would have first up there would be the code segment, then you would have the data segment, then you would have the block started by symbol segment, then you would have the heap and the stack. So if you write that out, this would be the code segment, put seg, and then next would be the data segment. Then next would be the BSS segment, which is the block started by symbol segment. Next is the heap, and then down here is the stack. And then the stack is going to grow from high memory towards low memory, and the heap is going to grow from low memory towards high memory. And this is all by design, because the code segment, the data segment, and the BSS segment, those are all going to be static size. When we compile, we know what the size is. The heap, though, that's going to be dynamic memory. So dynamic allocations on the heap, we need to make it so there's space for it to grow. We don't want it overflowing other segments in memory. So we got to give it a lot of space. So the heap and the stack, we either keep them really far away from each other, but growing towards each other, or we have them growing in opposite directions. You'll see that on Windows commonly, or always. So we've got these different segments. So when you saw that reference to the instruction pointer, that's going likely beyond the bounds of the code segment into a different segment, like the data segment, where initialized variables and such would be stored. So if we go back over here, look what it's doing. It's saying load the effective address into RDI of what's at this location. And it tells you that location right there on the right. If the debugger can determine something for you, sometimes it'll help you out. So one thing we can do in a debugger, of course, is set a breakpoint. So we can either set a breakpoint on the address or a symbol name and then an offset. In this example, we're inside the main function, and you see the main function plus offset 0. This is the very first instruction, push RBP. And then you see these different offsets as we go down, and the offsets are different. It's not always 1 or 2 away. Sometimes it's 5 away. Sometimes it's 9 away. That's because x86 64-bit is a variable length instruction set. It's not bound to 2 bytes or 4 bytes like ARM and thumb instructions. It's variable, which makes it so return-oriented programming attacks are very good for us because we can index into any offset anywhere within the code segment as long as we know what the address is, and we can have whatever byte is there interpreted as the opcode it would be. It doesn't even have to be a legitimate instruction. We can index into any offset. One nice thing we can do, yeah, VMMap is great, but sometimes VMMap doesn't work. It depends on your extension. So if I say VMMap, see how it's saying no? It depends. So you can also say, what is it? I think it's proc and then the memory map that way. We'll get to it in a moment here. But going back to here, let's set a breakpoint. I'm going to say break and then asterisk because we're giving a pointer. We're saying main plus this offset 4. So we'll just say plus 4. Now we've got the breakpoint. Again, if you know GDB, you know all these commands, but a lot of people don't. So I'm going to show everything. If we want to know what our breakpoints are, we can say info breakpoints, and we can see them. If we want to delete it, we can say delete the breakpoint. It's pretty self-explanatory. But now that we've got a breakpoint set, we can say run, and the program runs, and we hit that breakpoint where we set it. If we want to see where we are, we can say examine, X stands for examine, as an instruction, what the instruction pointer is pointing to. So this is the virtual memory address of the main function plus offset 4 from the base. And this is the instruction there. And these are the operands and operand values. So again, we're loading the effective address into RDI of RIP plus 92. So right now, if we look at RDI, so info reg RDI, 1 is in there. If I say SI, which sets something called the trap flag in the eFlags register and steps 1 instruction. We're 1 instruction further now. Now we can look at RDI and you can see what's been loaded in there. Is that address that we expected to see. That's likely going to be a string from the data segment. So we could say examine as a string RDI, and it says hello world. So hello world is that's the string that we know is going to be printed out to us. And then after that instruction, if I say disassemble, you can see where we currently are, and we're loading 0 into the accumulator register, and then we're calling printf. So that is an argument that's being passed to printf so that it knows what to print out. And then there's a NOP instruction after that, which says no operation. It doesn't do anything. It's used for like timing operations, padding, and things like that, or hacking sometimes. And then down at the bottom here is the procedure epilogue. Just like the procedure prologue sets up the stack frame, the procedure epilogue tears down the stack frame. So very, very simple program, as you can see, of course. So let's drop out of here, because that's about as boring as you can get with things. And let's go back into our complex program here. And now we can change it. So if we just did something like change this to int, The only thing that's going to do likely is return back a 0. Let's just take a quick look though. So we'll compile this one. The only change we made was change it from void main to int main. So we'll run this, put it in the debugger, and then disassemble main. And there you can see it's exactly that. NOP is now not there, and we are moving 0 into EAX because that's the AT&T syntax. That means we're returning, because the accumulator register is what returns back something from the called function to the caller. So in this case, we're returning a 0. We're saying everything's good here. Things went as planned. And then we return. Then the program will just exit out, of course, at this point. So that's not very exciting, but it is showing you the difference. So if we go back in now, and this time we'll start using the argument vector and argument counter here. So this, I'm going to use it. We can use it for a couple different things. One thing is we can, if we want to have a usage statement, maybe we want to check to make sure that someone passes in an argument. Like if you're a program and you're expecting someone to pass in an argument, you can use the argument counter and vector to handle that, to validate that the person did in fact pass in the argument. What if somebody passes in too many arguments? Well, again, you can use the argument counter and vector to see how many arguments were passed to make sure it's the right number of arguments. And then we can take them all in. They're all going to come in as strings, so we can typecast them as something else like an integer if we need to. Maybe we want to check to see if the user ID is 0, because you have to be root to run a script. So we can use the appropriate function to go and do that. So let's go ahead and set this. So I'm just going to say int argc, so it's an integer. And then after that, we're going to say char and then star argv. So the argument vector, it's just going to be a pointer to an array of pointers, because each of the arguments that we pass in need to be at a location that we can access. So we can index in to the argument vector and access the appropriate argument, as you'll see as we go forward here. So all we've done is that so far. Next thing we're going to do then is let's do a little check and say if, and then we'll say argc is, let's just do less than, this is a greater than 1. So if it's greater than 1, then what we want to do is print hello world then. Oops. So if the argument counter is greater than 1, no, we won't want to do it that way. Let me try to think this out. So I want to, if somebody passes in something, I'm going to actually say printf hello, and then we're going to take in the argument from the argument vector. So we'll say hello, and in here we'll say %s as a string /n. I forgot to show you something I wanted to show you before as well. But right now we're saying if the argument counter is greater than 1, because the argv0, you're always going to have one argument, and that's argv0. That's the program name itself. And we'll see this in a moment. I'll show you how to find it. And then argv1, which is a second, is going to be the name that someone passes in. So if someone passes in an argument, we're going to print that out. If they don't pass in an argument, then we're going to just default to printing hello world. So helps if I think of what I want to do before we actually go ahead and do it here. So now we're going to take in argv1 as the argument there, and that's what's going to be printed out as a string. And then here we're just going to say return 0, and then we'll close that one out, and then we're going to say else. So else, what we're going to do then is, I don't know, I think I need those, but I'll just say printf hello world. And this time I'm intentionally not going to put a, no, I am going to do that. I'm going to put a /n there intentionally. So I want you to see something silly. I could have just put a return 0 outside of it, but who cares? And then we're going to close that out. Helps if I use the right bracket here. All right, see if it yells at me. All right, so I have an error in there. I'm not looking at the comments because I know someone's like, you did this wrong. You put that thing in there where you weren't supposed to. And I say, I know. I knew I shouldn't have done that to begin with, but I'm so used to putting those parentheses in there. All right, so now we've got it loaded up again. So we're going to go ahead and open this up inside the debugger. And if we disassemble main, first thing I want to show you is, look how much longer it is this time. So it's definitely much longer than it was before. And one thing that I specifically called out is, look at that right there. Call quad word puts. I didn't use puts. I use printf both times. And on the top one, it does call printf. On the bottom one, it doesn't. Let's go back and verify in the code, right? Yeah, so the bottom one, I use printf. The reason is it parses through. It's like compiler optimization stuff. It looks through and says, you are using a /n for a new line, but you're not using a format specifier or format string. So we're going to optimize and we're going to roll over to using puts, because puts automatically does a new line. And again, you're not using a format string. So it changes it. But if we took away the /n, it would probably default to printf and leave it alone. It's just weird things you'll see sometimes like that. I don't think zero optimization will change that. I think it still does it, oddly enough. So let's get back out of here and go back inside of GDB and set the disassembly flavor to Intel. Another thing I want to show you, if we say disassemble main, I didn't show this before. If we say /r first, it prints out the opcodes. So before I referenced the base address of the function main, and then I told you that below that, those are the index offsets. So the push RBP instruction is only a 1-byte opcode. So 55 in hexadecimal in x86, 64-bit, means push the base pointer. The next instruction down is 3 bytes long. That's why after that one, it goes to 4 instead of 2. And that one says move into RBP RSP. So this is what I mean by variable length. Return-oriented programming is when we can get control of the instruction pointer. We can index into any offset we want and interpret that byte right there as code. Those bytes that I have highlighted, that's part of a different instruction. That's not supposed to be executed by itself. But if we index to that offset and we've got control of the instruction pointer, we can have that interpreted as whatever opcodes that would be disassembled to. Now, typically in return-oriented programming, we want to end with a C3 byte. C3 is ret, or return, or we can do jump-oriented programming and other stuff. But I just wanted to show you kind of that indexing and how that's interesting, that it's variable length. It doesn't default by printing out the opcodes because it's kind of messy on the screen, but /r will do that for you. So we say disassemble main without the opcodes. And now we've got a bunch of new stuff. We've got the procedure prologue up here, like we saw before. Now we've got a little buffer allocation. So we're saying subtract any, since the stack grows from high memory towards low memory, when we subtract from that address in the stack pointer, we're actually allocating memory on the stack for like a buffer, or to like store local arguments or variables, not arguments and variables. In this case, we are needing to store some things on the stack. We're not copying data into a stack buffer or anything, but we still need some space on the stack. And the compiler determines that for you. You don't have to worry about that typically. It bases it off your code. We'll do a proper buffer allocation soon, though. Okay, so we allocate a little bit of buffer space on the stack. Now, the next line down says move whatever's at RBP -4, load that into RDI. So we're going to set a breakpoint at main +8 here. So break main +8. And we're going to say run. So we get to that breakpoint. And there you can see we're at the move, whatever's at RBP -4 into RDI. I mean, EDI. Sorry, the other way around. I switched it to Intel. Jeez. Move into the base pointer +4, whatever's in EDI. So if we look at what's in EDI, it's 1. that ends up being the argument count. We didn't pass in an argument. So there's always going to be one argument, which is the program name itself. So we're writing 1 onto the stack at -4 from the base pointer. Right now, if we look at -4 from the base pointer, so examine GX, which is giant. G means quad word. So x/GX, it means examine 1 giant in hexadecimal. And then we're going to say look specifically at the base pointer -4. And what's there is that at this moment. But notice that it's EDI. So EDI is not a full 64-bit register. That's the lower 4 bytes of the 64-bit 8-byte register. So we could say instead WX, I didn't mean E, and we get that. So we're about to write the 1 there. So if I say step 1 instruction, we set the trap flag, we go 1, and now we look at that spot, and you can see 1 has been written there. So that's the number of arguments. It's just argv0, so there's only 1 argument. Now the next thing that's going to happen, let's take a look. It says move RSI and write it to the base pointer plus 16 bytes. So it's hexadecimal, so 1016 bytes, right? So we're going to the address that the base pointer is pointing to plus 16 bytes, and we're writing what's in RSI register. So if you look inside RSI right now, info reg RSI, that's what's there. We're about to write that to -16 from the base pointer. So right now, if we look at -16 from the base pointer, that's what's there. And now if we say step 1 instruction, you can see what's written there now is what was in RSI. Great, so let's go back and look at RSI again. So info reg RSI, and we know that that's being written onto the stack. Okay, what's at that location? So if we say x/GX, what's at that location? That's what's stored there. It's another address. Okay, what's stored at that address? We should be able to say something like pointer, and then we're going to dereference and typecast it string, and then we're looking at ESI, RSI. No, what did I mess up here? If anybody sees my error, please go ahead and tell me there, even though it takes a moment to show up. Oh, you know what it probably is that it doesn't want it to be brackets. It wants it to be parentheses. Syntax, always the syntax. So anyway, if you're curious about what this command is doing, we're dereferencing and typecast as a string, basically, whatever RSI is the pointer that's stored there. So we're going to where RSI is the address there, and it's a pointer to something else, and we're dereferencing that. And so if we run this, you see what it's pointing to. It's the program name itself. So that's argv0, basically. So argv0 is what the address of a pointer to argv0 is being written onto the stack at -16 bytes from the base pointer. So hopefully that makes sense there, and I didn't mess that up too much. All right, so what we've done so far, we've looked at the argument vector, and we saw that the first thing that gets written is argc, which is the number of arguments. It's only 1 because we didn't pass any. It's just a program name. And then the next thing being passed is a pointer to the address of the path to the program name, basically. So where are we at now? We are compare the double word pointer RBP -4. So we know it's there. We wrote 1 there, and now we're comparing 1 to that. If we go back to our source code here, and we say vim hello.c, it says right here, if argc is greater than 1, print hello, else print hello world, and what's it taking argument vector 1 that we passed in. So basically it's this check right here. It's saying, is the argument counter, is it greater than 1? If it is, we're going to print out hello and then taking the argument you pass and print it out as a string. Otherwise, we're going to go down here. So it's the decision. It's an edge that's being checked. It's a comparison, right? So if we drop out of here and we look at that again, we are checking the argument to see if there's any that were passed in besides just a program name. So that is going to be, when that gets checked, the comparison, it's going to have to say then, oh, are we jumping if not 0? Are we jumping on 0? So let's see where we're going next. If we say step 1 instruction, first let's look at the flags actually. So info, reg, e flags. So these flags are basically, you can look at them. You can go and look and see exactly what they are if you go and Google the bits in the e flags register and what each of them are. Each binary digit position maps to the different flags, like negative flag, carry flag, trap flag, 0 flag. There's a bunch of them. And when we see these decisions being made, like we're about to, which says jump if not 0 or jump on 0, it's checking those flags to make that decision. So right now, you can see we're at the comparison. Let's step 1 instruction. Now the comparison has happened. So let's take a look at the flags now. See how the 0 flag is now set? Because it was true. Because we compared RBP minus 4 to 1. They were equal. So therefore, it set the 0 flag. And now the instruction we're at says, jump if less than or equal. So jump if less than or equal to 1. So we're going to take that jump because now if we go back to our source code, this check just occurred and it's telling us to jump down here because we didn't pass in an argument. If we did pass in an argument, we go and execute that code. So that's why we're taking the jump. All right, so again, let's look at that. We know the 0 flag is set, so we're going to take the jump. So if we step 1 instruction, we're going to go to this address. See how we're at that address now? And then we look at the code here. It says load the effective address, whatever RIP plus A5, what that address is, load it into RDI. That's going to be the address of the string hello world. We already saw that. So if we say step 1 instruction, now we're at the call to puts. So if we say examine as a string, what's inside RDI? That's hello world. It's being passed as an argument to puts. Now let's go and enter an argument. So if we restart the program and I say, hello, what do I want it to say? Jim. I don't know why, but I'm putting Jim. And it says restart the process. Yes. We hit the breakpoint in main. So where are we? We are right here, back at the beginning again. So right now it's going to write the argument counter, which is stored in EDI, to the base pointer -4. So let's say info reg EDI. 2 is in there this time. Remember last time it was 1 because we didn't pass in an argument. So the only argument was the program name itself. Now 2 is going to be written to that stack position. Great. So step instruction. The next instruction that's going to happen here is we are going to take what's in RSI and write it to -10. Now that is probably going to be the program name again, like we saw the last time. So let's say step 1 instruction. And now we're saying compare what's at RBP -4 to 1. It's the same thing as last time, only this time there's a 2 stored there. Just to validate, we can say x/wx $RBP -4. And it's a 2 there, right? So this instruction comparing 1 to that is not going to be true. So if you look at the flags, that's the only flag set right now. We step 1 instruction. The 0 flag did not get set like it did last time. So since the 0 flag is not set, this jump if less than or equal, we're not less than or equal because we're 2. We're not less than or equal to 1. So now we're going to go into that other printf block. So if I say step 1 instruction, and now we see where we are, you can see we're actually inside here now. We didn't jump all the way down to the other call to puts. We're actually in this block now. So what I've highlighted right there, if you were to look at this in a recursive disassembler like Ghidra or IDA Pro or others, you would see that code right there, at least part of it's one block. This right here above it, that would be an edge. So that would be the end of a block, because that's where a decision's being made. You're either going that way or this way. Great, so we're down here now, and we're simply gonna go and grab the offset in memory where the argument we passed in is located. So Jim is going to be stored somewhere, and that's now just going to be printed out to the screen. So I don't think we need to walk through all of that, because it's just more of the exact same thing we already been doing. But hopefully, again, very basic reversing. We're taking hello world and we're just amping it up a little bit. And now if we want, we can even add in a buffer and do it that way to see if we can maybe cause a little buffer overflow real quick. But then I want to look at a call to malloc to show you something on the heap as well. All right, so let's drop out of here. And take a look at our code again. So what I want to do now, I got to think about it first. I'm going to create a little function. And this function, I want it to take in the argument, but then I want to do something that you normally wouldn't do. I want it to stir copy that argument into a different buffer that I'm going to create, or a different variable that we'll create here. So to do that, let's think about this. I'm going to create a little function. We'll just call it, what do I want to call it? Doesn't really matter, but I'm having trouble coming with the variable I want to use. Let's do just, I'll call it tchar. Why not? That doesn't make it confusing at all. So if we do that, that's going to be our function. Actually, I'll call it something different. Don't ask me why I'm using that. So I'm going to create a function here, and what we want to do now is take in an argument. So if we take in this argument, we want it to come in via standard in like we were, but we want to pass it to this function that we're creating here. So I'm just thinking out loud. All right, so let's just call this, and open this up. What I want to do in here is say char name. I'm going to create a little guy here. All right, let's do char name 16 bytes, and then I'm going to want to do something stupid, which is stir copy. So if we stir copy, and I'm sure I'm going to make a mistake and have to fix it here, but stir copy into name our argument, and then we'll do a print all right, again, I'm sure I'm going to screw something up here, but let me just think. And then we're going to say if the argument count is greater than 1, this time we're going to call that function that I gave a terrible name to. And we're going to pass it argv1. So we don't want to pass it the program name, of course. Again, I probably screwed something up, but let's see if it compiles first. Also, I'm going to have to add another header in here, so probably should have done that first, but it'll yell at us. All right. So let me go back over it. Oh. Cool. Yeah, I'll definitely do some heap stuff. I did do some Linux heap exploitation, actually a couple of those. I did a remedial heap exploitation one, which shows you how to go after when the safe unlink protection is not there from a long time ago, kind of introduction to Linux heap exploitation. And then I did another one, which was an off by one vulnerability that was a heap exploit because you could overwrite the size field of a chunk of memory, causing it to go back into the wrong Tcache bin. So I showed example of Tcache exploitation. So both of those are up there, and I'm going to. Yeah, I always explain this. This system here. This is my sometimes teaching system that is not allowed to do very much. It's very much not a good system. Everything I run in virtual machines in here, but the host is not a good one. And the reason I have that is there's a bunch of issues. Whether it be the magnifier when I want to use it crashes IDA in certain ways if I don't have this as a host, down to some of the different cards that I use, like the Proxmark weird extensions and stuff that I've written and worked with. They only working on the certain drivers on the hardware on this box that can't be upgraded. So yeah, don't threaten me like that. All right, so let me go back to seeing what the problem is here. Inputs a function declaration. Oh, it doesn't like that. All right, let me go back. All right, so we're calling pprint here. And we've got arg. Oh, it doesn't like the fact that it didn't tell it what that is. Sorry, I'm trying to look at the questions as well as they're popping up here, because I know I missed a bunch of them. So I'm taking an argv. Anybody see the error in the code if you're watching here? I know it's something simple. Oh, thank you. Duh, man. Yeah, that's a silly little problem there, right? Thanks. All right, so let's try that again, see if it yelled at us about not having a header in there. Yep, that's what the program expected. So string.h we're missing, so let's go back up to the top. All right, so we run this again, and it compiles. So the only difference now is we allocated a buffer, or we should be setting up a little buffer there. Let's actually, I missed one more step, didn't I? Let's go back and check one more thing real quick. No, that should be fine. All right, let's just try it. So GDB. All right, disassemble main. This time you can see there's a call to the function pprint here, so we can say disassemble pprint with a terrible name. And now we're disassembling that other function. So we have two functions now instead of just main, of course. Right here is that buffer allocation. Remember before it was just 1, 0 in an earlier example, now it's 3, 0, because we have created something new, right? And we're going to copy into that location the data that's being passed in via argument. So if we go in and say run now, and we simply just say an argument like Jim again, you can see it says hello Jim, no issues, just like before. But if we say hello Jim and just make it really long, then what we get is stack smashing detected. That's because there's a compiler protection called stack canaries. which is adding a little variable to protect the stack. It's checking and protecting the base pointer. If it's one there, it's protecting the return pointer. I'll show you what it looks like real quick, but right here you can see the function call to it. So if you fail the stack check, the canary, it calls this function. Right here is the check. It's saying grab the canary off the stack from -8 from the base pointer, move it into RCX, and then XOR this location here, FS segment register offset 28, is the stored canary that it's XORing against RCX. So if we overwrite that canary, then we're causing a violation there. If that protection wasn't there, so if we dropped out of here and we compile it again, but this time we say minus F&O stack protector. This time, if we do the same thing, run Jim and give it a bunch of bytes, this time you can see it says segmentation fault. So it didn't say stack smashing was detected. That's obviously the example of how great it is when you've got these protections if you're trying to defend your applications. If the protections aren't there, it makes it a lot easier for an attacker. Like right now, it didn't actually go. So older debuggers, older versions of GDB would actually return to the address and let it crash. Newer versions of GDB don't actually return to that address and show you that. So if we look at the instruction where we currently are, info, actually examine as an instruction, RIP, you can see we're at the ret quad word right there. So that's the instruction we're at. So if we're going to return to what the stack pointer is pointing to. So we can say x/gx RSP, and that's what we would have returned to, 4D, 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 that's our M's. But newer versions of the debugger don't actually return to the address. It's telling you were going to seg fault. But that's possible because of a couple reasons. One, the stack canaries aren't compiled in this time, and also we're using stir copy with no bounds check there. And it's not like if you use something like strn copy, for example, if we go in and say, well, let's change it to that or something even better. And now it also wants us to give it the size argument. And we could say size of something, or we could statically put the number in. This is where we get ourselves into a lot of trouble. And it's one of the things, when I talk about more advanced exploitation, I always pick on memcopy. And the problem is because memcopy often is getting its size argument from some dynamically constructed value. And oftentimes that value is something that can be influenced by user input, not user input like something like a command line argument or that simple. Something like, take the example from SIG-RED. Remember that DNS vulnerability from years ago? That was an issue on the heap where there was an integer overflow leading to a heap overflow. And one of the problems is that memcopy expects an unsigned integer as the argument, like an unsigned 32-bit integer as the argument. And if somebody can influence that value and make it a negative value, for example, like FFFFFFFF, well, -1 to memcopy is 4.29 billion because it's unsigned. So that's going to cause a massive problem. So again, my point of this being that depending on how the size argument is being constructed, oftentimes people think, oh, but we're using a function that has a size argument, so therefore I should be safe. It all depends on how that argument is being constructed. But that's just a simple example of showing you something with an overflow condition there, that there's plenty of videos on YouTube about how to exploit that type of vulnerability. I've even done one myself before. So let me quit out of here. I didn't save that one. And let's do a different one, this time with malloc. So let's do a call to malloc on the heap so I can talk about the heap for a little bit. What time are we at here? 12:15. So many times writing a driver would help a lot. Recommending resources. Yeah, there's damn vulnerable Windows driver out there. There's like some good write-ups about actually writing that driver and making it vulnerable and learning about ioctl codes and how to find the ioctls and things like that. But that's, yeah, damn vulnerable Windows driver. If you Google that and like type write up or something after it, you'll find some good hits there. So let's do a different program now on the heap. And we'll talk about the heap a little bit. So I'm going to create a new program called my heap. And we'll go in and say vim my heap. All right, so let's try to not make mistakes this time. It's too time consuming. Include, let's go ahead and put the ones I need. I need standard, lib. I'm going to need standard IO. I'm going to need string.h. That's probably all I need. If we need something else, I'll go and grab them. All right, and now we're going to say, I don't want to return anything back because I don't care at the moment. And let's just get right into it. All right, what I want to do is, my goal is to call malloc and show you what the heap chunks look like. And we'll also use, let's use memset and maybe print out the heap and things like that. So, and I'll show you what the chunks look like and some other things to look for. And just another example of something you want to watch out for as well. So let me just finish coding this real quick. So int, we're going to do a malloc call. Let's do 200 bytes. Actually, we'll do 20 times the size of the pointer here. Not pointer. All right, let's say print f. Now, what I want to do here is I'm going to, if we only call malloc, it's not going to do a check to make sure that the allocation request was successful or not. So I'm going to add that in. There's a lot of ways we can do this. I think heap alloc and stuff on Windows, depending on what you're using, will do it for you. But I'm just going to add a little check in one simple way to do it. We'll just say memory. So what I'm saying there is if pointer, if it's not 0, basically, if I actually get an address back. So we're going to say if pointer, printf, memory successfully allocated. And then we'll say memset. Actually, I'm not going to memset yet because I want to show you what happens if you don't memset and just something you might want to watch out for. Let's close that out. And then we're going to say else. And then printf memory failed. I think that should be good. So that should compile. All we're doing is calling malloc with this size here. So let's do that. And let's compile it. So we'll say GCC no pi. I think there's something else I wanted to do, and I can't remember what it was that I wanted to do. Let's see if something else pops up. So I'm going to say no pi. We'll do, I don't care about stack canaries right now. All right, that compiled, no problem. Let's go ahead and take a look at it. So right now I've got PETA loaded. I'm going to actually kill that right now. I don't want to use it. We're going to do a session on Jeff coming up soon, which is a really awesome extension. All right, so disassemble main. All right, so here's our call to malloc. So malloc is a function that allows you to allocate dynamic memory. So memory on the heap. Let me explain the difference between stack and heap memory real quick. When you allocate stack memory, typically that's reserved for function calls in most cases, right? Every function call gets its own stack frame. We talked about that. And the main function's there. If main function calls another function, the stack frame for that called function gets built on top of the main stack frame. And there's something called the procedure prologue and epilogue that handle setting up the frame and tearing down the frame based on the calling convention selected. So functions are used for like finite operations, right? If I want to not repeat my code all over the place and I just want to call a function to do some arithmetic, like a calculator function that adds two numbers together, I got to pass it some arguments. It returns back to me the sum or the product, whatever, and it's done. It doesn't store anything. It doesn't preserve anything going forward. You get in, you get out. But if we want something that's going to stay in memory, like object-oriented programming, and we want to instantiate an instance of a class. So we have like a dog class, and I want to be able to instantiate an instance of a dog, and we can select the attributes like the breed of the dog and the gender of the dog and the fur color. And then I also have my methods that come along with it, like my commands like sit, bark, or speak, roll over, lay down. Those are all the functions that I want to travel around with this object once we instantiate it. So that object's going to live on in memory until we kill it. Now, when are we going to kill it? Well, if you're like Microsoft and you use C++ smart pointers in a really weird way using the invasive method, then there's going to be a reference counter that tracks the number of references to the object. And once that reference counter decrements to 0, that object's going to be automatically destroyed. It's going to be freed and sent back to the heap manager for recycling. But if it's something that's not using something like smart pointers, you got to track that object and you have to know when you no longer need it. Another example would be if you're using a browser like Chrome, because you use all the memory up on your system, right? And you leave up a window in Chrome that's a PDF document that you're reading. As long as you leave that PDF document open, that memory is going to stay resident in use. So if you just leave that window open and you've got a 20 meg PDF, that's going to stay resident. That is not going to be on the stack. It's going to be on the heap, because until you move to a different URL, that memory stays in use. And when you go to a new URL, something has to free that old memory, give it back to the heap manager, which goes on something called a free list for recycling so that you can reuse that memory and stop committing more memory and resources from the kernel. I did do a session on the heap. Like I said, it was specifically on heap internals on Windows, where we primarily talked about ptmalloc2, which is the most common Linux heap allocator that you'll see. We also talked a bit about dlmalloc, which is an old one, jemalloc, Jason Evans malloc, tcmalloc, which is Google's thread caching malloc, phkmalloc. There's a bunch of them. And they're all doing different things to manage the heap, sometimes sacrificing performance for security or the other way around. So I've done talks about that in the past. You can check out the channel for that. But what I want to do right now is I want to set a breakpoint on the call to malloc so you can see how it's a bit different. So we'll say break on main plus that offset to the call to malloc, which is 13. And we'll say run. All right, so we hit the breakpoint. And we are on the call to malloc. So malloc, all it wants as an argument is the number of bytes that you want it to allocate. There's also calloc, which is another one. Calloc will allocate basically an array of any number of chunks of the same size. So you can say, I would like 10 contiguous allocations of 200 bytes each. And you get returned back a pointer to the very first allocation, contiguous in memory. So calloc is another commonly used function on the heap. Memset is another one. I'm going to use that in a moment. So malloc just wants an argument, which is a size for a dynamic memory allocation. Calloc, you can specify a number of allocations of the same size. Then there's free. Free wants you to pass it in a pointer to the chunk that you no longer need, and it will return it back to the heap manager, and it gets put on something called a free list. And there's different types of lists. There's fast bins, there's Tcache bins and stuff like that as well. there's a default arena that gets created on Linux. We call the heap an arena. So the main arena is kind of like the process heap that starts up. You can have as many heaps as you want. I mean, there's a limitation. It has to do with if you're 32 or 64-bit times the number of cores on your processor. And that's going to determine how many arenas you can have, as well as subsegments within those arenas. There are things called sentinel nodes. We typically call them. The sentinel nodes are the list heads, basically the heads of the free list, so that it can track chunk sizes of similar size, because you want on the heap things to be as clean as possible. So if I want an allocation of 100 bytes, we don't go look at a free list that's too small to be capable of holding 100 bytes. There's just ways in which that works. Again, I did a session on that, and you can learn a lot more there. We've got this breakpoint. When you call malloc, what we're expecting is the return back to us in the accumulator register will be a pointer to the allocation, the chunk. So if we want to look at the stack right now, we should be able to see the argument to malloc, which is the size, or it might be in a register. Let's take a look. So I'll say disassemble. That just shows me main. So disassemble. Yeah, that's fine. So disassemble main, right here, you can see it's going into a register. So it's not going to be on the stack, because 64-bit, we like to put things in registers because it's safer there. So we're moving hex 50 into EDI. Well, you can do 5 times 16 and you can see what that value is, right? It's basically the size that I asked for. I did 20 times the size of an int. And that will then tell malloc how many bytes we want allocated. When we return back from malloc, the accumulator register should then hold the address of the allocation. So right now, if I say info reg RAX, that's in there. If I say NI, so SI sets the trap flag and you go one instruction, you step into. So if I say SI, we would step into the malloc call. I don't want to step into the malloc call. It's boring. So NI says step over, basically, and then we'll be on the address directly after the call to malloc. So next instruction, and you can see I'm right there on 589. So now we take a look at the accumulator register, and that is going to be the address of my allocation, hopefully. So let's take a look. So let's grab that, and we'll say examine, and I'll say 8GX. So examine 8 giant, which is 64-bit in hexadecimal, starting at that address. Now that's what it prints out. So it's all zeros right now. What if we look after that? Let's do 20GX. So that's what we're seeing. One last time, let's do 40GX. Cool, nothing that exciting there. Now, if we want to see the metadata for this chunk of memory, we would say subtract 8. 8 because that's 64-bit, right? And look what's there, 61. That is the size field of the chunk. Every chunk has a structure associated with it, and there's metadata on the front of every single chunk on the heap. It's not very complex, but what we're seeing right there is the size field. Now 60 is the actual size that I requested, most likely. So why is there a 1 there? Well, what it actually ends up doing is padding out, typically to the next D word boundary, so that it can have control over the least significant bit, and that's called the previous in use bit. The previous in use bit allows us to say whether or not the adjacent chunk in lower memory is in use or not. If it's in use or doesn't exist, then it's going to be set to a 1 here, like you see it. If the adjacent chunk in lower memory was actually a chunk that was once in use but now freed, that would be a 0 instead of a 1. The reason it does that, again, if you look at that other session I did, you can learn more about it. There's a rule on the heap because we don't like fragmentation. And there's a rule on the heap that says no 2 free chunks are allowed to be adjacent in memory and free. We coalesce them into one bigger chunk to reduce fragmentation. That's a back-end allocator thing. Most heap implementations have a front-end allocator, like the fast bins on Linux, which used to be the look-aside list on Windows, low fragmentation heap. Those are front-end allocators. And the reason front-end allocators are useful is, or the reason that we like them is because it takes less code execution to get an allocation from a front-end heap allocator. Because the assumption is if it's a chunk that's on the front end allocator, it's stored there in some list, then it's a commonly used chunk size. We don't care about fragmentation on front end because it's something that's commonly used. Like for example, on Windows, the original LFH implementation, the low fragmentation heap, before we got into the segment heap and such in the kernel, the low fragmentation heap had a rule that said if a size has been requested 18 times or more, you initialize LFH to service that chunk size going forward. Because if it's a size that's always needed, then don't worry about fragmentation because it's so often needed. But if it's a size that's not often needed, we do worry about fragmentation because we want to have good performance. I'll give you a quick example of when that would get triggered. Let's say you're looking at a web page like CNN.com, some news site, and you look inside the HTML. So you view the HTML. You're going to see all kinds of things like buttons and div elements, span elements, table elements. Those are going to be things that are constantly used. And there's always a static size associated with those objects, those elements. So if you were to look at a browser and you look at something like creating a C button, there's a class associated with that, a C++ class. It'd be called C button class. So C button : inside there is going to be a function that's going to be the function to create the object. When you go to create the object, there's going to be a static size that is the size for C buttons being passed to the heap alloc function. And either the process heap or the isolated heap gets passed as a heap argument. So again, all of these C++ browser objects that we're creating with HTML and JavaScript have a static size. Span elements, div elements, they're always the same size. There might be attributes that are different sizes, but my point being that LFH would be servicing those requests. We would want to service those requests with the front-end allocator because they're so commonly used versus the back end. So there's a lot to the heap, but I just wanted to show you here that this is the metadata of this chunk, which is the size field. And there's different flags in there. Like I said, we take the size requested, we pad it out to the next boundary so that we have control over the 3 least significant bits. Those are going to be the bits responsible for the previous in use flag, which is the lowest bit, the is main arena flag, whether or not you're in the main arena or not. And then the other ones, I think it's the mmap flag, where you create it via mmap or SBRK. So those flags become important because if you look at another session I did on off-by-one exploits, what we did was we used an off-by-one vulnerability to overwrite the byte in the size field, enlarging a chunk, causing it to go back to the wrong Tcache bin, allowing us to eventually get exploitation or code execution by messing with something called the free hooks or the malloc hooks, basically debugger stuff that lets us get code execution. So the thing I was hoping to show you though here is, let me disassemble again. And if we go down to this exit call, so let me go to this exit call here, say break. Oh, it didn't work. There we go. Continue. Okay, we hit the breakpoint and it says memory successfully allocated. If we go back and look at that chunk, see all this data down there? So this is interesting, right? So this data down here wasn't there before. That ends up being the data that was printed out via the puts function call or the printf function call. My point of showing you this is there's a function called memset that if you don't set memory and initialize things to something else, a lot of times old data gets left behind And often we can examine what old data used to be there. And there's been things like, what was it? It wasn't Poodle. There was another really big uh, crypto vulnerability that came out many years ago. But one of the problems was that old keys, old encryption keys, were left in memory because it wasn't being set. Meaning that, like, think about this: if I allocate memory on the heap because I need it for something, but that something is something secure, what I need it for is something like that I want to protect. And then we go and free that data, we free the chunk because we don't need it anymore. If we don't clear it out, that old data is still going to be there until it gets recycled and something else overwrites it. So that's why functions like calloc will automatically memset everything to 0. You need to clean up after yourself. A lot of times when you look at information disclosure bugs in Microsoft, like Windows, when you see how they patch it, often you'll see memset gets called, and that's the patch, because they're cleaning up something that was leaking out something important. And I'm not saying it applies directly to this one. It's a silly example. Like if we go down here and say, what is that? Grab that address, say examine as a string, that address plus 8, memory successfully allocated. That's an old string data we don't need anymore. So we could call memset, we can get rid of that stuff. So I'm not saying it's always going to work. Let's try it though. In this simple program, it might not work, but let's quit out of here. And let's just go in and use memset real quick. All right, so probably not going to work, but it might. Actually, it should work. Why wouldn't it work? All right, so I'm just going to say memset, and then we're going to say PTR 0x41. We're going to memset it to all A's, and then 20 times size of pointer, right? And that should be good. So let's compile this, see if it works. We go back in with the debugger. And now let's do the same thing as before. I'm going to set that breakpoint that I had. Oh, it's not there. I got to disassemble. So we set the breakpoint on the call to exit. So let's do that again. Break main plus 82. And I also need the breakpoint on the call to malloc so I can get the address of the allocation. It's going to be different each time because of ASLR. So break main plus 13. We say run. All right, we hit the breakpoint. Next instruction, now RAX holds my chunk address. So info reg RAX, there it is. We can grab that. Debuggers, by the way, by default, ASLR gets turned off sometimes, so keep that in mind. But you can always turn it back on. And I'm going to say examine 20 giant hexadecimal starting at that address -8, so we can see the metadata. Okay, there it is. So that's the metadata. Again, it's a size field. And this chunk, nothing's happened yet. So if I say continue, we hit the next breakpoint. And now let's look at that same location. What I'm hoping is that it's all A's now. See how it's all A's, and that old data that said printf, like with the printf stuff with the string, is gone. Because that old data was there because it took up the space earlier on. It got recycled, I guess, and now we just overwrote it. We memset it to something else, so we're not leaving behind traces of something that could be sensitive. Just a silly little example I wanted to show you. But that's a lot of stuff we covered there. I think it's a good time to stop as well, because we've been going for like an hour and a half. We looked at, like, what my goal of showing you stuff today was, let's go to the beginning. Let's look at hello world. Let's look at basic disassembly. Let's walk through the argument vector encounter and see how we can just simply reverse this stuff. And if we run into an instruction we don't know, we can go and look it up. And then we did a little function call, and then we used stir copy to cause a vulnerability in there, and then we did a heap thing. So just a little bit to show you around. The next time I do this, I want to have more of a purpose. The other thing I showed you was statically linked versus dynamically linked, and that's something important as well. There's a mitigation called relrow, which is relocation read only, and that is a mitigation that protects something called the global offset table. So remember I talked before, if we say info functions, no idea why it's hanging right now. All right, let's drop out and let's go back in and say info functions. See how these say puts at PLT, memset at PLT? Those are dynamically linked dependencies. If you want to be able to run my program on your computer, you have to have the shared objects, the libraries that have those functions in them, because they need to be linked at runtime. If you don't have those functions, then there's a dependency issue. So what happens when you link is there used to be something called lazy linking, and it's still there. Depends if rel-row is not on or if it is on. Because the way in which linking works on Linux is strange. It basically says the first time we go to call a function, like let's say the call to malloc. So if we say disassemble main, here's that call to malloc, right? That's our very first call. So the first time we call malloc, it says call malloc inside the procedural linkage table, which is this address. So we go there and say examine two instructions starting at that address. And what it says is jump to the quad word pointer at this location. This location right there is something called the global offset table. So right now we're inside the procedural linkage table entry for malloc specifically. Every dynamic dependency has its own entry in the procedural linkage table. Every dynamic dependency also has its own entry in the global offset table. So this address we're going to jump to right now is the global offset table entry for malloc. The first time we go to call malloc, though, it hasn't been linked yet. So the linker has to be called. The linker gets past a symbol name, finds the address from within a shared object, kind of like get proc address does on Windows, and then it writes it into the global offset table entry. So right now, if we look at the global offset table entry for malloc, it says can't access memory at that location. So the program's not even running yet or anything. But either way, it's not there. So if we drop out of here and we say obj dump minus capital R and then my heap, these are the global offset table entries for each function. So malloc right there, this is the address of malloc's entry in the global offset table. So how it works is we're in the code segment, we hit the call to malloc at PLT. We go to malloc's entry in the procedural linkage table. It says jump to the pointer inside the global offset table entry for malloc. The first thing that's going to be stored there is a pointer, likely back in to the procedural linkage table or to a dynamic linker code that's going to then go link it and then write it to this location. And then the problem is, since it's a writable table of pointers, we could potentially, as attackers, hook it. We can, if we get a write what where primitive, we can overwrite one of these pointers in the global offset table so that when it gets called, we gain code execution. This was a super popular attack technique that we used to use all the time on Linux. But nowadays, most of the binaries you run into are going to be compiled with rel-row protection, which is going to harden that table so that it's no longer writable. Everything gets linked right up front. It's no longer lazy. Like, that's interesting stuff to keep in mind. There's like so many different techniques over the years that we used to rely on and depend on that work perfectly, and then they get mitigated by these exploit mitigations or other ways that they do it. And they kill an entire bug class that way. So it gets harder and harder as we move forward. That's why nowadays you see a lot of these exploits are very one-off. A lot of heap grooming and different things going on there, but still possible. I always get asked that question: is it still going to be possible in the future? Yes, it's just harder, right? It's always going to be possible, most likely, but it's just harder. Stack overflows should still not be possible today. I mean, most of the time you can't do it because there's mitigations like canaries and such, but the fact that you could still do it is ridiculous. 30 years ago, people were saying this isn't going to be working much longer. We're going to fix this. And it's still possible. But then you've got protections like shadow stacks and control flow enforcement technology that has branch protection that's really going to finally put a stake in the heart of return pointer overrides and return-oriented programming. So again, it ups the ante, and the mitigations get more and more expensive. I'm not the mitigation. I mean the price of exploits gets a lot more expensive out there. So let me stop there. I know I've been going for a long time. We'll look at the questions. If I missed your question, I apologize. I know I wasn't very good about looking over. Type it up now. I'll hang out for a little bit and we can chat. I'll talk about some answers, and then we'll call it. And then next week, I'll come up with a different one. Maybe next week, you tell me what you're interested in too as well. Like we can look at IDA Pro or Ghidra, probably IDA because that's what I'm more familiar with, but still it's disassembling the same way. And we can do some of the same things. We can maybe look at a Windows binary or, take a look at that stuff. So, all right, let me see. Future of exploit development research. I mean, that's what I was just saying. It's a lot of people, when stuff got really hard, as it's gotten, moved over to car hacking, moved over to medical device hacking, moved over to IoT hacking. There's nothing wrong with that because that's an attack surface that needs to be addressed, and it's getting better. But the golden years of hacking, I like to say, was back in like the 90s and the early 2000s. The golden years are long in the past. But if you kind of want to go and be able to relive some of that, going after these IoT devices and new attack surfaces that are showing up, a lot of times those same mistakes are being repeated. But as far as like sticking with the hard stuff, like Windows 11, modern system, fully patched, all that stuff, I'm going to have Connor McGar on again pretty soon. We've been talking about taking a look at one of the more advanced mitigations like virtualization-based security and HVCI, and how you might go about trying to figure out how to beat that. Because in the past we used to get kernel code execution on Windows all the time, and we do token stealing via a ROP chain of code execution. But now you can't usually do that, so we get read and write primitives, and that's usually enough to be able to steal the token so it still works. We can still get around it. And then they go and try to kill the previous mode technique that we love to use, or the HAL dispatch table plus overwrite technique that we've used for years in the kernel. And then you got to find different wings, like U rings and things like that. Like oftentimes there's a way to get it to work. It just takes a lot of work. And sometimes there's just not a way to get it to work. It's tough. But that's why you see 7-figure price tags for these exploits. So any tips on landing a vulnerability research internship on no U.S. citizen clearance? Yeah, I mean, obviously the intelligence agencies and stuff, they have those programs. I mean, I've seen things like IO Active has had those before. I don't know if they still do it every year, but I know IO Active in the past each year would have internships. I think Exodus Intelligence used to do that. I'm not sure. I don't think they require clearance. Maybe some do, some don't. There's still maybe check out IBM X-Force. They might do internships. Same thing with Palo Alto. I know they've done internships in the past. Google has their stuff sometimes. They have their contests and internships. But yeah, off the top of my head, I don't know of any like great ones that do internships. I mean, I used to have interns work with me where I had my fuzzing farm for browsers set up, and basically there's just so many crashes happening that I didn't have time to triage everything. And the thing that we would do is the person helping me out would go through the fuzzing farm results, because each time a crash would occur in the browser, some post-mortem script would take a snapshot of the VM in that state, so we know which mutation of JavaScript caused the crash. And then a lot of times it's just garbage bugs, like they weren't useful, but I taught them how to do that, how to triage it. And then if it's something useful or it looks good, then their value is watching or working with me while I weaponize it or try to weaponize it. So sometimes you'll find people that are looking for stuff like that, but it's not always the easiest thing. Yes, it is recorded. It'll be up there. Right after this, it'll be posted on YouTube. Again, the reason I do this live streaming is so that we can do the Q&A, and so I make mistakes, like the silly mistake where I forgot to put a char in my declaration. It's pretty sad, but we all make those mistakes. But I think it's better this way. The thing that is not so great this way is that we don't have a nice clean video. We don't have like different angles of me talking and my face in the front going like the world's collapsing, and then really well edited stuff, which all looks really nice, but that's very time consuming, and these videos are way too long for that. So yeah, WinDebug, there's no end of commands. There's a never ending set of commands. Like that's the cool thing about WinDebug is there's a lot of cheat sheets out there, and you watch some really talented Windows people like Alexander Ionesco, and you see the commands and you're like, well, I didn't know you could do that. And you like document those commands, but it's really, really cool stuff. You can use them in WinDebug. I've done quite a few in WinDebug. Like last week, I think it was last week, I did reverse engineering some mitigation and we used WinDebug. What mitigation was that? Oh, export address table filtering. We went through taking a look at that mitigation to see how it works. And then I've also done kernel debugging on Windows with WinDebug. Obviously, WinDebug's the only one it works. And we looked at stuff in there too. Connor McGar came on before, so did Chompy, and we were doing stuff there. Jonathan Ryder's been on with me. We did kernel debugging together. So like, there's a lot of those up there, but I'll definitely be using WinDebug in the future. Super interested in exploit research for those interested in Windows 11. Where you're learning, yeah. I mean, I'll just others please answer that as well. But like, definitely for sure, if there's still it still makes the most sense to start off if you're new to kernel exploitation. Start off with something like the damn Windows vulnerable driver and look at the walkthroughs other people did. And again, that's why I always pull out Virgilius, the Virgilius project, because all those crazy kernel structures, tons of undocumented stuff. But you really, if you want to go down that rabbit hole, get the Windows internals books, start learning about all those structures like E process, K process, KPRCB, KRCB, E thread, K thread, just all these structures and how they all work together, like redoing, even if it's something from Windows 7 or Windows 8, redoing the research somebody did and actually getting the exploit to work. That's going to serve you greatly. I don't recommend just diving straight into start with, oh, I'm going to go after virtualization-based security and figure out how to go exploit LSASS since Mimikatz isn't working anymore because Credential Guard. Like, good luck with that. Maybe you're a savant and you can do that. IDA parsing C how to make your own stuff. Yeah, yeah, Jonathan. It's funny you say that because in the session last week, I found some structures that weren't documented because they were part of payload restrictions.dll, and one of them I think was a structure that was the library load address. So the library load address of interest, and this was export address table filtering. So you need the library load address that you're protecting. So like NTDLL. The next one was the instruction pointer address at the time of the guard page violation. So that was another part of it. And it called a function to get the base address of wherever that's coming from. And then the next one was the size. Size was there as well. Maybe size for both. And then there was some ulong. I can't remember what it was, but it was a struct. And like, that's exactly, I think that'd be a fun one, building an IDA, that kind of a structure, and see how it helps you a lot. The other big structure was G, so global lib state, mitigation library state. It was a global structure. It was massive, but that's going to be a tough one because I don't think you can actually probably get exactly every field. But if you want to do that with me, let's figure out that structure, Jonathan. That'd be a good one. What else here? Would I recommend iOS, Android? So, I mean, honestly, right off the bat, my head says Windows and Linux versus mobile, and I'm assuming you're talking about like binary exploitation and like jailbreaking the thing so you can get those 7-figure bounties. The information that's available out there is so tightly held to the chest. Like those exploits are worth so much money, 7 or 8 figures, meaning millions or even over $10 million potentially, if you have, and yes, those people do get paid that. And if you have that knowledge, like look at the iOS blast door, right? The whole mitigation focus on iMessage and the fact that you can send stuff that gets rendered or parsed by iMessage, and that's 0-click. The person doesn't even have to do anything. They had to put protections there. So if something does happen there, that it's isolated. So that attack surface, when you see something like 7 exploits chained together to root a phone, that's extremely difficult. So I would say Windows and Linux is going to be a lot easier than doing that. But by all means, if you've got a good group of people to start that research, it'd be awesome. Global idea to get reverse shell in Linux with ROP, return to libc or got. I'm not I'm not sure I follow. I mean, return to libc is a really old technique released by Solar Designer back in like 2001. That when it works, it's great because you can just return to a function within a loaded library. ASLR is still going to be on, but that's going to be mostly stack exploitation stuff, which is probably not going to be possible with canaries and all the guards and mitigation. So most of the stuff that works is heap related. The stack stuff, though, you can find opportunities. It's going to be most likely on the heap. And return-oriented programming, while we can still do it, until those shadow stacks get implemented and control flow enforcement with the end branch protection, by all means, ROP is going to be the preferred method. Once that gets killed, obviously you got to move towards other oriented programming techniques like jump oriented, right? So we're not depending so much on the ret instruction, but we can also do something like pop something or load something into a register and then jump to that register or the address in the register to get around the dependency on the return. But there's different ways, of course, that we can go about doing that. CET bypass, at least getting a little deep. Well, I mean, control flow enforcement technology, like I'm assuming you're talking about this. I'm typing on a screen right now. So end BR64. Like that's end branch 64. And the idea there is that when the return instruction gets executed, the address that you're returning to must hold an end branch instruction. And if it's not, you get terminated because that means someone's trying to do return-oriented programming. So if that's what you're talking about with CET, getting around that is going to be probably not real possible for the most part when it comes to that type of exploitation or that particular technique. That's why I was mentioning jump-oriented stuff and such, because that's going to get you away from that dependency on the ret instruction, because that's what that's doing. It's the control flow enforcement is really focusing on ret for the most part. And I'm sure there's focuses on jumps and calls and things like that too. But it's just like control flow guard. CFG really minimized the number. Well, not it wasn't super effective, but it's pretty effective. It took the number of ROP gadgets that are usable and shrunk it down a lot, because now there's a bitmap, and I forget the block size, but like let's say it's a page of memory. So each page of memory is separated into a different block in a bitmap, and the address range in there has to have a function entry point, or else you can't call an address in there. It can't get down to like precision where it's every single address, because that would just be too much overhead. But putting it into blocks where if that block has a function entry point that exists, then you can call into that block. So it just reduces the number of usable gadgets in that case, but it's similar in that way. But yeah, I would love to. If I mean, I haven't seen much CET stuff out there, but that would be cool. Um, exploit 401 training goes into it. I haven't done a course. Exploit 401 goes into CET bypass. I'll have to check that out. I haven't seen it. I know that I think it used to go into arbitrary code guard bypass by like, or import address table filtering bypass things. Like you can get around arbitrary code guard and a lot of these mitigations in exploit guard by doing things like messing with the imports table and then leveraging hooks and instructions that you can get used to clear flags and stuff like that. Same thing with like the old SMAP bypass techniques, where there'd be a control register in memory that if you could clear the flag in there, then like ORing it or something, then you could turn off SMAP or SMAP. And those types of things are possible sometimes. And I haven't seen anything specifically for CET, but I guess like I said, the heap stuff, CET is not really going to be as big of an issue. But I guess the only bypass then that comes off the top of my head would be doing other oriented programming, like I said, like jump oriented programming instead of return oriented programming, just getting away from that dependency on the ret instruction. Absolutely, that would be. I guess I wasn't thinking of that as a bypass, right? It's just like an alternative technique to avoid it versus a bypass or like disabling the mitigation. But if they actually have figured out a way to use the ret instruction and be able to get around CET, I'd be very surprised, but that'd be awesome. Talking AFL and fuzzing. Yeah, I've been talking to a couple people I mean, I could do fuzzing too, of course, but like I like to have guests sometimes who, like, if I know someone like they're just a freaking expert in this one area, I like to have them on. Like that's why Kuba Gretzky's going to come on to talk about Evil Jinx because I think he probably knows it better than I do. So like, why would I not want him to come on? So he's coming on March 1st, and we've got the individual who owns Jeff coming on mid February. But I was talking to Richard Johnson before and some other folks. I'll keep working on that and do some smart fuzzing. If I don't find someone, then yeah, we can do something where we can do some Dynamo Rio action, use Frida and stuff like that, and do some fuzzing for sure. Yeah, the imports table is what the imports table is writable on Windows, so that's how we can hook. This is why if you look at the way that Exploit Guard implements some of the mitigations, I think, and don't hold me to this, the original version of like Emmet, the Enhanced Mitigation Experience Toolkit, they did hook the imports table, but they have a control called import address filtering to prevent hooking, because the way that works from a high level is if you overwrite an entry in the imports table and it's like, let's say you're trying to call heap alloc. Well, heap alloc is supposed to be in kernel base. I'm making that up. I don't know, but let's say it's in kernel base. It validates that the function that you're calling is within the address range of the module it belongs to. So if you hook it, you're now out of bounds and get caught. So the way that they actually do the hooking now, which is nothing new, is instead of hooking the imports table, actually hook it at the beginning of the like hot patching basically, right? Where you go to the very first instructions and you put a little jump up there to hook it that way so that you're not messing with the imports table. But then you're modifying the code. All right. Assistance of AI that 0 days will not exist anymore. That's I mean, right now AI is very helpful for 0 days because I've said this before. I've been using it to look at really complex pseudocode. The first time I used it, I was looking at Microsoft Terminal Services, and I was looking at all of these different functions that utilize obfuscation and encryption and encoding, and the size calculations for the calls to memcopy were stupid complex. I mean, really complex. So I took the decompiled code with hexrays, give it to AI, and man, it an amazing job helping you determine how that calculation is being made, which makes it a lot easier for you to then go write your custom client and start trying to mess with things going inbound to see if you can affect the size of the argument with memcopies. Like AI is helpful in that space, but yeah, I mean, obviously they're going to get better and better at finding vulnerabilities and doing things on our behalf. So hopefully we'll be retired by that point. All right. Yeah, Jim H. Jeff, like I said, I'm having Chris, I forget his name off the top of my head. I'm so used to his handle that I forget the name, like most people. But he's coming on February 16th. The guy who maintains Jeff, who wrote it. So I'm looking forward to learning some stuff there too. But cool. All right, I think it's time to call it. But really do appreciate you guys hanging out. And I know kind of went long here. And some of this was probably really introductory for you. But again, I wanted to start at the beginning because there's a lot of people out there that it's nice to be able to get some of that information that I mentioned, like even stuff. The one that always sticks out to me, and I'll just type it up on a screen real quick on my terminal. I've said this so many times where I would see FS colon 0x30, and I never knew what that was. I'm talking 20 years ago. I didn't know what it was, and like I couldn't find out because Google wasn't giving the answer back then. And knowing that, okay, that's the offset within the thread information block that you dereference to get the address of the PEB. That's how shellcode finds kernel 32's load address. Oh, like putting that glue in there is really helpful, which is again, it's why I like to do it live. But thanks, appreciate it. SP, I do plan on at some point, I want to do GDB debugging with a Cisco router because I think I've done that. I haven't done it for a while, and it's neat to look at that, but not that specifically though. Cool. All right. Well, I will see you next time. I'll figure out what I'm going to show next week. And again, this is going to be on YouTube soon. And yeah, that's pretty much full time what I do besides doing a curriculum lead at SANS for course authorship and such. Cool. All right. Have a great weekend. We'll see you next time.